The final aspect for our refinement model M2 to discuss would be its relative DLF freedom. And we already introduced to you about what a relative DLF freedom is earlier when we spoke about refinement model M1. So I'm going to refer you to the earlier slides and also lecture videos for the details or introduction to relative DLF freedom. But for now, I'm just going to focus on formulating the sequence of DLF freedom and also assign to you some exercise to do. It turns out proving the relative DLF freedom for our M2 is trickier than how we prove it for the DLF freedom for M1, which is natural because we actually got more guards and also more invariants to be included in the sequence. But I'm going to talk about it in just a moment. And this will be the model answer for the sequence that you should really formulate for the relative DLF freedom for M2. You should really grab a piece of paper, try to formulate yourself to see what the sequence should be, and then compare your answer against mine. That's what I would recommend. But for now, let me highlight certain parts for you. So we talk about the abstract model, first refinements M1 over here, and also we got the concrete model M2, the current refinements. We got M1 and M2. Specifically, I try to put all the events together. So this might be a nice point to summarize about what events we have. From the earlier refinements, we got ML out, ML in, IL in, IL out. And so far, we got 1, 2, 3, 4, 5, 6, 7, 8. 8 events. To start with, IL in, ML in. So these are the two events that are not impacted by the traffic lights, so they stay the same. And also we got two new events, MLTL green, ILTL green. And also we got the split events for ML out. We got ML out1, ML out2. We also got the two split events, IL out1, IL out2 for the IL out events from the abstract level over here. That means when we try to formulate the relative DLF freedom proof obligation, we have to include the guards from all the events over here, all the 8 events. That's why I try to put them into a single place. Okay, and this part over here for the hypothesis is really straightforward. That's just about including the axiom, including the invariants from all the levels, from model 0 to model 1 and also to model 2. Right? That's the part we just did earlier. What I want to mention is about in the hypothesis, we are really supposed to put the disjunction of the abstract guard. As to why, you can definitely refer to the earlier part for M1 discussion. We spoke about why you should really put abstract guard disjunction over here and the concrete guard disjunction in the goal over here. Let's take a look at very quickly. In the case of the abstract guard disjunction, so that should really include the guards for all the events. So we got ML out over here, ML in, IL in, and IL out. So that's exactly the guard you actually saw, right? So these are the 4. This one corresponds to this. This one corresponds to this. This one corresponds to this. And this one over here corresponds to this. What about the concrete guards? The concrete guard is going to be something like this. It's going to include MLTL green guards, which will be exactly over here. The ILTL green guards, which will be exactly over here. And also we got the MLR1. MLR1 over here. And also MLR2 guards, which will be over here. And also we got ILR1 guards. And also we got ILR2 guards. Okay, over here. Okay, I think I made a slight typo over here. I'm going to fix it. This part over here should be not equal to 1. Okay, it's a very small thing, but I just spotted it. Okay, I'm going to fix it. Okay, when you see the slide, you will see the updated version. And finally, we also got the guards for IL in, ML in. The guard for IL in over here, the guard for ML in over here. Right, so that's about the proof sequence you have to formulate. And let's now move on to about its proof. You will start with this giant sequence over here. And there will be several exercises for you to do. I already laid out the proof tree that you're aiming for. And however, to really go from the initial sequence into this pink sequence over here, I put ... over here. So that means it will be your exercise. So this will be exercise number 1. Let me put here. So this will be exercise number 1. you ought to find out the sequence of inference rule that can really transform from this one here to this one over here. This will be exercise number 1. And to really go between these two intermediate pink sequence, that will be exercise number 2. And really to go between these two, it will be exercise number 3. And once you go to this final pink sequence, you will be able to complete the proof as follows, like this, right? That's what you should really also convince yourself as well. For this final sequence, it will be provable by following this sequence of inference rules. And so there are 3 exercises for you over here to really complete. Alright, so that's about DLF freedom, and we just finished discussing the final aspect for our refinement model M2. Let's now try to summarize about this latest refinements. Alright, so let's now take a look. We have our abstract model, refinement number 1, and also the concrete model, refinement number 2. I put them side by side. We can make some quick final comparison. And just don't forget about the same correctness criteria for proving the validity of the refinements. God strengthening, invariant establishment and preservation, convergence of the new events, and also relative DLF freedom. And of course, don't forget about the exercises we assign to you, because for this second refinement, many of the steps will be simply identical to what we did for the refinement number 1. So that's why I only try to brush up quickly about the details, and you will need to fill in the gaps by completing the exercises. Let's talk about variables to start with. You can see over here, this part over here is the variables for refinement number 1. And what do we have? We have A, B, and C, which replace the variable n from model M0. On the other hand, for the concrete model M2, we actually got this many variables, it turns out. Let's take a look. Let me put it in pink, and we'll look at each one of the variables very quickly just to review. To start with, you can see here we got A, B, and C, which inherits from the abstract model, the first refinements. And we got these new variables over here. For MLTL, ILTL, these are simply the new notion about traffic lights. And ML pass, IL pass, remember what they are for? They are for ensuring the new events not diverging. Right? And what's really the refinement scheme that we have? Meaning that we are reusing the variables from the abstract model rather than just replacing all of them. So it's called superprecision. Let's just remind ourselves this term over here, superprecision. Okay. And in terms of the event, I'll get to the event in a moment. In terms of the invariance, okay, if you look at the invariance over here, the typing constraint, we just got MLTL, the traffic light, ILTL, the traffic lights, and also we got the conditional invariance, which is more interesting, and that's the exercises we did about what it really means when each of the traffic light is actually green. That's something you can refer to the earlier part of the lecture. Invariant number 5 is really our introduction earlier as the fix in order to really fix the invariant preservation unprovable sequence. That's something you can also refer to the earlier part of the lecture. And what about the remaining part? The remaining part talks about ML pass, IL pass, and also their property. That's really for the divergence freedom proof that we did earlier. Okay, so what I'm going to do is I'm going to isolate all the model components that are to do with divergence or lifelock freedom. Let me use the blue. Okay, so start with, for the variables ML pass and also IL pass. Right, so these two variables are really for using to control the interleaving of the two events, namely MLTL green and also ILTL green. Whenever you talk about divergence, you have to focus more on the new events. And for the invariance, it will be number 6, number 7, number 8, and also number 9. And of course, we got the various different usages for IL pass, ML pass, right? You can just see the color, right? So that's something I also went over with you earlier. And don't forget, in order to prove about formally that your system is actually divergence free or lifelock free, you have to use the so-called variance expression. That's what we said before. So out of these, the blue ones are really to ensure about divergence, freedom. Divergence, freedom. Right? And let me just also mention about the events over here. For MLOut, the abstract version, it has been split into MLOut1 and MLOut2. And for ILOut over here, it has been split into ILOut1 and ILOut2. And what's really important for you to remember, which we analyze in detail, is about to distinguish between two cases about the car leaving either the island or the mainland. And you can see here, for example, we got different cases. Okay, we got A plus B plus 1 not equal to D versus A plus B plus 1 equals D, in which case we have to turn the traffic light to be red. Symmetrically, we got B not equal to 1 versus B equals 1, in which case we have to also turn off the traffic light to disallow any further exit of cars from the island. Right, so it's a very quick walkthrough about the events and also invariants and variables that we spoke about in this current refinement number 2. Right, you should really study and review carefully about everything we said. And of course, there are certain gaps which we didn't really talk about in this particular refinement, but of course they are similar. They should be done in a very similar way as the first refinement. So for the exercise you are assigned to do, you are advised to really complete it. Alrighty, so that's about all the discussion I want to make for refinement number 2, and we are now done with all the models I want to discuss this semester for the bridge controller. For the remaining part of the semester, maybe about 2 or 3 lectures, I'm going to talk about another example, which is about a file transfer protocol.